transfer by J.P. Holman, Holman, which is as famous a book as Frank White. This book will also give you material properties such as thermal conductivity. The problems given to you are numerical in nature. In a day or two, I will also send you solutions, not of all problems, but some problems. So, a typical geometry we study in 1D is a slab of some thickness L. Usually we set up the coordinate system to go from the left plane to the right plane. So, x goes from 0 to L, and the governing equation which is equal to 0. Now, let me also simplify the material further. Let us say that for this course, heat generation term is also 0. So, if you have problems related to heat generation in what I have sent you, you can ignore them. So, whatever be the boundary conditions, the solution will be of the form A0 plus A1x, where A0 and A1 will depend on the relevant boundary conditions at x equal to 0 and x equal to L. Similarly, if you have an annular region, then this governing equation, you have to work with the Laplacian in radial coordinates. Which is TRR plus 1 over R TR, if you use suffix notation, or incidentally, you will notice that the steady state temperature distribution does not depend on material properties, but with boundary conditions, material properties will come into picture. That A0 plus A, you can see d2t dx square does not have any thermal conductivity in it. That means the steady distribution, whether you have wood or copper, it's the same variation. But heat flux depends on thermal conductivity, because it's k times the derivative of gradient of temperature. So, how do you solve this problem? So, here you write, you combine them, or just to be consistent. So, dt dr is C1 over R, and T is equal to C1 log R plus C2. So, whatever be the boundary conditions, you will have a logarithmic profile. Of course, if R equal to 0 is a part of the domain, then C1 has to be 0. Okay, so, in a solid cylinder, T is constant. So, the only permissible temperature distribution in a solid cylinder at steady state with no heat generation is T equal to constant, which is equal to the outside temperature, the boundary condition. So, these constants are to be determined from boundary conditions. Okay, we had an example of a composite slab. So, this is region 1, region 2 with some boundary conditions. So, 1 is given as K1L1 and 2 has thermal conductivity K2 and slab thickness L2. So, you have d2t, let us say this is x. So, d2t dx square is 0 in 1 and 2 in both regions. So, in 1 t is equal to a0 plus a1x and in 2 t is equal to, let us say, b0 plus b1x. So, this problem requires you to find 4 constants a0, a1, b0, b1. So, you have one boundary condition on the left plane x equal to 0, you have one boundary condition on the right side, which is applicable for material 2. So, at the interface we use, like in the interface problem of 2 liquids, we have temperature continuous and we have the heat flux continuous. So, in 1 the boundary conditions would be x equal to 0, let us say t equal to T1, not always, but this is a kind of a boundary condition. Then x equal to L1, let us say temperature is continuous, that means T minus is equal to T plus. Then here x equal to L1 plus L2, T is equal to T2 and x equal to L1. So, the boundary condition at L1, those are the interface boundary conditions. This is the interface. Minus k dt dx on the right hand side is equal to minus k dt dx on the left hand side. Okay. So, it is not that you apply interface conditions to the same region. While working with region 1, you have made left temperature equal to right temperature, and while working with region 2, you have made the right heat flux equal to the left heat flux. So, the solution is this. So, you can evaluate dt dx is just A1 if you are in region 2 and I mean if you are in region 1 and B1 if you are in region 2. Okay, those can be substituted. So, you will have a system of 4 equations for A0, A1, B0, B1 and these can be found. So, the boundary conditions will keep changing from one problem to another, but the basic form of the solutions remains the same under steady conditions. So, just a note on boundary conditions. So, let us say this is the interior of the solid and this is the exterior. So, a boundary condition is stipulated on the surface S. So, you could have T given. This is an isothermal type of boundary condition. Some students who have exposure to differential equations and Laplace del square t equal to 0, t given. They said, is it a Dirichlet condition? I said yes. But in our context, it is isothermal. So, or the other type of condition is that Q, so equal to gradient of t. This is the other type of boundary condition. So, you may want to write it as Qn equal to minus k times the derivative of t with n. So, if q is given, then what, this is a boundary condition in terms of a derivative, and of course, if q is 0, that is an insulated condition that makes the derivative of temperature on that surface equal to 0. So, suppose you have a slab problem and your left side is at temperature T1, right side is insulated. You can quickly see that, well, the temperature profile has to have 0 gradient, which is possible only if T1 is constant everywhere. So, T1 and 0 flux will make the slab have or attain constant temperature. These are familiar results and also easily understandable. In fluid flow, it is not as obvious till you build some experience with it. But temperature is a very, very familiar variable, physical variable. So, if you have q in the x direction, will be minus k times the derivative of t with respect to x. Okay. So, just to give an example, let us say q is given here, then at x equal to 0 minus k dt dx, the partial derivative is what I have written, but t is only a function of x. So, this is also the total derivative is equal to q. So, when you apply on the right hand side, you will get q pointing in the x direction. Okay. So, the third possibility is what we call the convective boundary condition. The convective boundary condition, you have fluid flow happening outside. So, you have to solve Navier-Stokes and energy equations in the fluid medium, heat conduction equations in the solid phase, and match them by interfacial conditions. That is a very hard problem to solve. So, the engineering approach is to employ handbooks. If your main interest is only in the solid medium, then the entire effect of fluid motion can be encapsulated through a convective heat transfer coefficient, parameter h, which specifies heat flux. So, on S minus k times this derivative is equal to T minus Tf, where Tf is a far field reference temperature of the fluid. H is the heat transfer coefficient, which is a positive quantity. So, H will depend on the flow field prevailing in that region. Okay. Okay. So, when you write this expression, H is representative of fluid motion in the exterior. So, S interior is a solid region, outside is the fluid medium. So, h is a parameter that comes from the outside world and k is for the solid. So, this k should not be mixed up with the fluid thermal conductivity, it is S. And this temperature is the temperature distribution in the solid medium. Okay, so, if this is a slab, let us say you have some temperature T1 here, some temperature T2, and at steady state it has to be a linear variation. And let us say Tf is the far field fluid temperature. So, in the near field, the fluid of course will have boundary layers and this and that, and then you will have some variation of temperature. You are not factoring in all those details. All that information is supposed to be contained in H. Okay. So, in a problem like this, at x equal to 0, T is equal to T1, while here x equal to L, you do not know the temperature T2, it depends on H. So, you have minus k times this derivative is equal to H T2 minus Tf. So, this is at x equal to L. Okay. So, if the same thing were to happen on the left side, let us say this temperature is given and you do not know. So, you are given a far field temperature. This is temperature T1, this is Tf, this is the x direction. So, at x equal to L, T is equal to T2, but at x equal to 0, you will have minus k times the derivative in the normal direction, which is in the negative direction. So, you will have k, so instead of n I have now written minus x is equal to H T1 minus Tf. Okay. So, where H has to be given to you, it depends on the flow field prevailing over there. So, here you may wish to say that n is in that direction. Okay. So, these boundary conditions will keep changing from one problem to another, but the form of the solution within is either linear for Cartesian coordinates and logarithmic for cylindrical coordinates. And the log term vanishes if it were to be a solid cylinder, because you can't deal with r equal to 0, where the log term is not defined. So, a new idea that was introduced, which is there in fluid flow also. In fluid flow, there is a ratio of what is the driving potential? You can think of it as pressure drop. Let us say flow through a tube. Pressure drop is the driving potential and the resulting flux is the flow rate. And the ratio of the two will be related to friction factor. Okay. So, friction factor serves as a kind of a resistance, but friction factor depends on Reynolds number. That means, the resistance depends on the flux and hence the pressure distribution. So, the idea of a fluid resistance is not very useful, because if you set up a network, it is a non-linear network. You understand that point? Because remember friction factor, you have to, please remember, because definitely you will have a question on friction factor. Okay. That means you have to use Moody's chart, which means you have to guess velocity. Okay. And then find Reynolds number, find friction factor, and then get velocity and see if your guessed velocity is equal to the velocity that you have calculated. If not, you guess again. We had talked about bisection and this and that. So, that is a longer calculation. So, fluid resistance can be defined, but not very useful from a calculation viewpoint, because it generates a nonlinear network. But here, let us say for a slab, let us say this is T1, T2, and you get a linear variation, which if you solve for will be T minus T2 over T1 minus T2 is equal to 1 minus x over L. This is the solution, right, a linear variation. Okay, so, like all potentials, the flux is related to the change in potential, right. So, everywhere it is not T1 per se does not appear, it is T1 minus T2, T minus T2. So, it is the change in like pressure itself does not play a role, it is pressure difference, right, delta P in fluid flow. So, these are all potentials of various types, and the change in the potential gives rise to a flux, either flow or heat transfer. Now, these fluxes are energy transfer rates, right. It is not energy transfer, it is not that 100 joules of energy have been transferred, it is an energy transfer rate, which is why there is a word rate processes in your course title. Okay, so, it is linked to change in potential giving rise to a flux, which becomes very clear here in case of heat transfer, but it is very clear to you because you have studied fluid flow earlier and you have attended all the lectures, at least this group. So, what is Q? Q is equal to minus K and this will be equal to minus K T1 minus T2 over L. This will be plus. The derivative is negative, so it is T1 minus T2 over L, which can be written in the form of a thermal resistance as T1 minus T2 over Q equal to L over K. So, this L over inverse of thermal conductivity plays the role of thermal resistance. It is like electrical conductivity, inverse will give you at least proportional to electrical resistance, and then you have a length of a wire over there, here you have the width of the slab, and it does not depend either on temperature or Q. The right hand side is a constant that makes the thermal resistance network linear. So, all the have you studied network analysis in some electrical engineering course? You may or you will or you have? No? Yes? So, that means you will study, right. I think next semester probably, 4th semester. Do you have an electrical engineering course? So, it will be network analysis. At that time you will remember what I said. Thermal resistance network similar to electrical resistance network, mainly because the resistance is constant, it is a linear problem. You can construct a fluid resistance network also, but it is harder to solve because resistances depend on flow rate. So, you have that trial and error procedure to be adopted. So, I want you to complete this problem. Suppose you have a composite slab 1 and 2, then Q is equal to T1 minus T2 divided by L1 over K1 plus L2 over K2. So, these are resistances in series. I want you to show this. How? We have done we have set up the problem earlier. you have to solve for the interface temperature, right? You have interface boundary conditions, complete that problem and get Q. Now, Q here, Q equal to minus k dt dx can be evaluated for any x, but it is independent of x. So, you may evaluate for x equal to 0. Okay, so you see that this is an example of resistances in series. So, you can also have resistances in parallel, which are given in the problem sheet I have just sent you this morning. Let us say these are two boundaries with temperatures T1 and T2, and you connect them like this. This is region 1, this is region 2. So, here the resistances are in parallel. Okay, so, if you want, so this is you may call this the equivalent resistance, R equivalent. So, you will have 1 over R equivalent equal to 1 over RTH1 plus 1 over RTH2, and then the heat flux will be T1 minus T2 divided by R equivalent. That will be the total heat transferred from one side to the other. So, these elementary ideas carry over for a slab geometry, but if you have an annular geometry, this is 1, this is 2. So, for the annular geometry there is a slight point of difference that arises from, of course, the shape of the object. If you have a slab, this Q per unit area is the same unit area crossing any plane, but for the annular geometry the area keeps changing with R. So, this Q is often written as Q into 2 pi r. 2 pi r is the circumference per unit length that we are talking about. Unit length normal to the plane of the blackboard will be unit area times Q, that is total Q. So, here the resistance is defined with respect to capital Q. It does not matter in case of a slab, because the same small q passes through all the planes of the slab. So, this turned out to be, I just gave you the solution, right, C1 plus C2 log R, C0 plus C1 log R. Based on that solution, this turns out to be log R2 over R1 divided by 2 pi k. So, the thermal resistance for the annular geometry involves the radius ratio, mainly because the heat flux crossing a plane, see, as you go from, let us say you heat from within, by the time you come out, the heat flux would have reduced, right, because you have it is the same heat flux. See, I hope you understand that steady state heat conduction is given by del square T equal to 0, which is really del dot Q equal to 0. Okay, so, you will have Q1, if you integrate this, Q dot N. So, you will have equal to 0. So, Q1 A1 equal to Q2 A2, and this A1 is equal to A2 in case of a slab, but not so for an annular geometry. So, which is why you have a radius ratio coming into picture for a thermal resistance. Now, Last time I had solved this problem, a slab problem where on the left side so this is T2, this is T1 and there is a convective heat transfer coefficient. So, when H is given, T1 is not known to you, it has to be found. Tf, the reference temperature, is what is given. So, you have hot gases like a furnace. So, if you have, this is the slab of the insulating wall of a furnace, you have hot gases inside at some temperature Tf. The gases are in a state of motion, they are all represented by some heat transfer coefficient H. Okay. So, the wall on the left side is getting heated up and then it will transfer some heat to the ambient, which is at temperature T2. Okay, that is this problem. Now, there are two possibilities. One is that you have water flowing through tubes contained in the wall. Okay, in that case, you want hot gases to heat the water in the tubes, so that you produce a lot of steam suitable for power generation, or it could be an insulating wall, in which case you do not want heat flux to go through. So, we had solved this problem. So, what are the governing equation? So, T is equal to A0 plus A1x. X equal to L, T is equal to T2. At x equal to 0, we have k dt dx equal to H T minus Tf. Okay, so, you can solve this problem and find A0 and A1. Now, one can assign a thermal resistance to the heat transfer coefficient also. See, this H is causing a reduction in Tf from Tf to T1. It is a reduction in Tf. So, you can think of a resistance in between the far field of the gas medium and the wall, that is the left plane of the wall, okay, which is, so this is x. So, in this case, the thermal resistance is defined as Tf minus T2 divided by Q. Okay, it is the overall temperature difference divided by the heat flux, total heat flux passing through the wall. Okay. So, when you do the calculation, it will turn out to be 1 over H plus L over K. Okay, so, this L over K arises from the slab and 1 over H arises from the convective So, how will you get this result? You just have to find A0 and A1 and then substitute, and Q is equal to minus k dt dx anywhere in the slab. You can also notice that the contribution of the convective heat transfer coefficient becomes small if H is very large, and H becomes very large when fluid velocities become large. So, if you have very intensely mixed region, okay, you are stirring it in some form, let us say, then U is velocity is high, H is high, and that resistance due to convective motion of gases will be small, which means that this temperature drop from Tf to T1, that drop will be very small. So, T1 will be practically equal to Tf. At the same time, if H is very small, then the thermal resistance will be very large. So, if you have a stagnant medium, then H is small, and you will have a considerable amount of temperature difference between Tf and T1. Okay. So, once again you see that the resistances have become additive, and 1 over H becomes the resistance equivalent to the convective heat transfer coefficient. So, now let us look at a generalized problem. So, let us say this is Tf1, here it is Tf2, here there is H1, H2, L1, K1, L2, K2, and even without solving the governing equations. So, in general you have to solve the governing equations, del square T equal to 0, first in slab 1, then slab 2, apply interface conditions, apply exterior conditions. So, linear variation in K1, linear variation in K2. What is the variation in the fluid region? You do not know, because the entire heat transfer process is contained in a single numerical parameter called H, but you know temperature is decreasing. That means, if Tf2 is less than Tf1, then the entire heat transfer is from the left side to the right side. So, this T1 will be somewhere here, and there will be an interface temperature. This is T2, which is slightly higher than Tf2. So, you will have like this, but linear variation inside the solid phase, the solid medium. Okay, so, how much is so now I write, so how much is the heat flux through this composite assembly? It will be temperature difference. So, it is like V equal to IR. How much is I? It is V over R, which is delta T, which is Tf1 minus Tf2. So, overall temperature difference divided by the equivalent resistance. The equivalent, which is 1 over H1 plus 1 over H2 plus L1 over K1 plus L2 over K2. Okay. So, thermal resistance is like a global analysis. This approach will not give you intermediate temperatures. For that you have to solve the governing equations. It is a global approach. It gives you the total heat transfer for the applied temperature difference. In case of an annular region, it will be log R2 over R1 divided by 2 pi K1. That is the resistance contribution of an annular region. Okay, so an example of thermal resistances in series. So, in the problem set that has been given to you, you are given a region like this, let us say 1, 2 and 3, and you have T1, T2. And I ask you how much is the energy transferred from the left plane to the right plane. So, you can combine 1 and 2, they are in series. That combination is in parallel with 3, and then that will give you equivalent resistance, and then T1 minus T2 divided by equivalent resistance is the total heat transfer. Okay, so these are simple problems that you can solve, but it will not give you the temperature distribution. For that you go back to the local formulation, which for heat conduction turns out to be del square T equal to 0. Going a step back, you know that surfaces will be exposed to a fluid medium. So, you will have mass, momentum, energy in the fluid phases, and you will have heat conduction equation in the solid phase, and these have to be matched at the respective interfaces. still have a few more minutes. Just want to illustrate one point of similarity with fluid flow. So, the analogy I told you, slab problem is like cuvette flow, which is, what is cuvette flow? It is Newton's parallel plate experiment. Just as a matter of curiosity, I may tell you, if it is Newton's parallel plate experiment, why do we call it cuvette flow? What is cuvette? Cuvette is the name of a person. Cuvette studied the stability of flow between parallel plates when one plate is moved relative to another. You recall flow through a tube. As you keep increasing Reynolds number, laminar flow suddenly becomes turbulent. So, that phenomenon is called instability. We discussed instability from the viewpoint of the dissipation capacity of the fluid medium. Now, Cuvette showed that this configuration, where one surface moves relative to another, is always stable. This is the fluid medium. It is a very important result. That means you have if you wait long enough, you will get a linear velocity distribution in that gap. That solution will not get disturbed. For example, in a tube, it goes from parabolic to the turbulent profile. You know, turbulent profile will have higher stresses. That means the velocity profile will become very flat with large gradients at the wall. That does not happen for this geometry. So, in honor of his analysis, it is called Cuvette flow, though it was originally used by Newton to define viscosity. So, here you remember that it takes a certain amount of time. For Cuvette flow, the unsteady part will last for a time. You remember time constant, which depends on, of course, this gap, and depends on if H is the opening, the unsteadiness will prevail for a time duration which is given by a time constant. How much is it? H square divided by which fluid property is it? Well, first of all, it should give you units of time. It can't be mu. Kinematic viscosity, which is nu. So, the unsteadiness prevails here for a time duration h square over nu. Okay. So, the same thing happens for a slab. Let us say this is T2. Let us say initially the slab is at some temperature T2. At x equal to 0, so this is all x. At x equal to 0, suddenly you heat the left surface. It is like giving motion to the top surface of this channel. So, x equal to 0, t is equal to T1 for all time t greater than 0, while the right surface remains at temperature T1. So, suddenly the left plane becomes T1. So, now you are looking at, well, this is also understandable, it is going to take some time for this wall to heat up, like the time it takes for the fluid in that Cuvette flow experiment to attain a linear variation. So, here also it is a linear variation ultimately. So, let us use green. This is ultimate, but at some time t which is less than that ultimate, temperature will evolve. Initially it is T2, it is cold, and slowly it will warm up till a linear profile is established. Okay. Suppose you want to analyze this problem and you ask how long will it take for steady state to be attained, then you have